Hey, IB2, how's everybody doing today? I hope you guys are enjoying your time at home today and miss you. I wish you guys were in school. So we're going to be doing a lesson right now on electricity. So I'm just going to use this time to go through the main ideas and show you what's going on with static electricity. All right, so what is electricity? Why does it exist? So this is when I would normally have you guys break out in some discussions and talk about what's going on with electricity here. You guys have probably noticed that electricity is something that flows through lines in your house and then comes out in the form of things that you want, like light or heat for a toaster. You put it in your phone. We do all kinds of stuff with electricity. You've probably even seen it in nature with sparks coming off of your finger when you touch a doorknob in the wintertime to possibly lightning coming out of the sky. So what is electricity and why does it exist? It's actually one of the four fundamental forces. It's the electromagnetic force. And we're going to go ahead and look at that with this unit. And that's really what static electricity is all about, checking out this force. So electricity comes from atomic structure. So think about what you've learned in chemistry and in your past science classes. In an atom, you've got your nucleus, which has protons and neutrons in it, and you have electrons coming around, flying around the outside of the atom. So the electrons on the outside are negative, and that's what they call their charge. They have an elementary charge of like a -1 for a single electron, whereas the protons inside the nucleus are positive, and they have a charge of +1. And when you look at the charge of an atom overall, you just look at the balance between your protons and your electrons. And if you have more protons, you end up having like a positive cation, or if you have more electrons, you have a negative anion. So that balance speaks to electrical charge. When you have an equal number of protons and neutrons in an atom, you end up having a neutral atom. And if you have an excess, then you end up having some sort of a charged atom. And that's where electricity comes from. So that's what we're going to look at with this meta effect here of how does a charged object lead to an electrical force that we can experience at the macro level. So what holds the nucleus together? So when we look at the nucleus of an atom, it's all positive. And we're going to learn here that positive charges will repel each other. So the thing that actually holds the nucleus of an atom together is the nuclear strong force. It's like an extremely strong force. We're going to look at this later. That's why it's called the strong force. But it's the thing that's responsible for keeping these protons just smashed together, really close proximity. They would love to just shoot apart, but they stay together because of this nuclear strong force. Notice that some of the rules that we look at here with atomic structure, protons and electrons, they're opposite from each other, so they actually attract each other. So when you have this really positive nucleus of an atom, it's going to attract those electrons. Now the electrons are moving extremely fast around in their orbits, their orbitals on the outside, and so they've got a lot of tangential speed, which would want to keep them from collapsing into the center. But then you also have this strong attractive force in the center too. And the further the electrons get away from the center, the weaker that force is. And that's what you get to this idea of like valence electrons. Electrons that are far away from the nucleus are more likely to fly off and shoot off and ionize. And this is what we call the ionization of an electron. So that's our basic atomic structure. And we will do a lot more of this later in the year when we get into nuclear physics too, just to let you know. So some big ideas that we're going to look at with this static electricity idea. One is called electric charge, and we give it the lowercase q. Electric charge is actually a quantized number. Quantized just means it occurs in whole number increments. Turn this off real quick if you guys don't mind. That's a little bright there. And so notice that this idea of whole number integers, it comes because really when we think of charge, it's actually made up out of whole numbers of electrons and protons. And because electrons and protons are individual things, they exist in discrete numbers of things, just like there's only 5 people in the room. There's not 5.36, right? Same kind of idea. So this idea of quantization right here, when we notice a charge, we give it the letter Q. It's equal to the number of protons or electrons times this thing called the elementary charge. The elementary charge, we kind of think of it in terms of like +1 or -1, but we actually have a number I'll put on this one real soon with you too. Okay. Now, in any sort of object, you're going to have this balance between these things, and you're going to see this idea of becoming neutral or having net charges on it. But the big idea to start with is charge is quantized. It exists in whole number increments. Another big idea we look at when it comes to statics is we look at this idea of conservation of charge. It just says charge cannot be created nor destroyed, but it can only move to one place or another. And so when you have a closed system and charge is moving around, in that closed system, you will never have a change in the total charge of that system as long as it stays closed. All right, another big idea, we're getting back to elementary charge here. So we said before that like for an electron, we give it a charge of like a -1, or a proton, we give it a charge of like a +1. But then we have a unit called the coulomb right here. And this coulomb gives us the charge of a single electron or a single proton, and it's going to be 1.6 times 10 to the -19 coulombs. Okay, and so if it's positive, then we give that charge to the proton. If it's negative, we give that charge to the electron. And in a one whole entire coulomb, so you notice this is just like a really small number of coulombs per particle. But if you take the inverse of this number right here, you end up getting this number of how many individual charges are there in 1 coulomb worth of charge. And it's actually 6.25 times 10 to the 18. And you can notice right here a little tie-in with our IB data booklet. Your Coulomb's constant is here in your elementary charge. We're going to get into Coulomb's constant in a second, but there's your elementary charge right there. Okay. All right. So here's a question for you to think about. I've got the answer down on the bottom here, but you want to work this out. So if you had a car engine and the battery was moving 3.75 times 10 to the 21 electrons through the starter rotor, how many coulombs of charge were moved? And so then you're just going to look at that relationship that we just looked at on this previous page to the charge per single, and then here's the number in 1 coulomb. So I want you guys to play with that idea, with the idea of getting to -600 coulombs. So you can see how that relationship works between particles, elementary charge, and the total number of coulombs. Okay. All right. Now that we started thinking about these charges now, so charges are going to be moving around when we exchange, when we put particles together, when we put objects together, and we put them in contact with each other. So we have this thing called the triboelectric series that says when you put different objects together and rub them together, what you end up getting is electrons, or possibly protons too. They can be rubbed off of one object and onto another, depending on their electron affinity. So certain kinds of objects would like to attract electrons to them more than other ones would. And so when you rub certain objects together, some objects are going to accumulate electrons that they rubbed off a different object. Now, depending on the type of material, there's different types of materials that we play with. Sometimes we use like clear acetate, which is like a type of plastic that's real hard and clear. And it has a tendency to become positive, which means it gives away electrons. And sometimes we can use something like polyvinyl, PVC, and that has a tendency to take electrons. Certain things like fur has a tendency to take electrons, but like cotton has a tendency to give electrons. And so we can mess with these things. And we can notice that there's a series. Certain things become very positive when they're rubbed against other things, which become very negative. And if you can locate things on the series and say, hey, if I was going to rub PVC to fur, what would happen? And you can see the PVC would pick up the electrons from the fur, and it would actually become negative, whereas the fur would become positive. Okay, so this idea of triboelectric series, we're going to play with this with a lab next class. So there's a video here to watch. You guys could check this out. This should show some demonstrations around this idea of using a triboelectric series to rub things together and the kinds of phenomena that you can get. Normally, this is something I would do in class, but I found this video. It's actually better produced, I think, than I would be able to do with my cameras and stuff in here. So I'm just going to have Bill and I show you some of the demos that I would have done in class. Okay. All right. So triboelectric series, there's a thing called John voltage here. You're going to play with this in your lab next class, but I just want to kind of point out some of the features. It's a pretty simple FET, but this guy's John Travolta, but they're playing with his name, John voltage. And what you're noticing here is that he's got his shoe and the floor, and there's like carpet, and then there's shoe surface like rubber. And when he rubs these things together, the foot that he's got, the bottom of his shoe, the rubber, has more affinity to pick up electrons, whereas this carpet down here, maybe it's made out of like wool or cotton or something, has the affinity to get rid of electrons. So when he rubs it, you can see he's gathering electrons. He's pulling these electrons off the carpet and into his body. Now, electrons are going to want to get far away from one another, so they spread out around his body. Kind of see that happening. But when he gives these electrons, which are sort of accumulated in his body, they've accumulated, so he's got a net negative charge. When he puts his electrons close to a grounded object, this is a conductor as a doorknob, and it connects to the earth, it's going to let these electrons escape each other. Because right now, John voltage is net negative. But when he touches the doorknob, you can see how it grounds those electrons. It sends them to the earth, and it makes it so that he can become neutral again. So objects really would rather be neutral in general. All right, so you got to play with that one. Just get it, but we'll look at it with the lab next class. And one of the things to note here is that it always requires work to separate charges. We've got this tool called a Van de Graaff generator that I'm going to look at with you guys. Hold on, let's pause here.
I will be sending an email here shortly that I need you to read before tomorrow, but I need you to make sure you take home any laptops or other instructional materials you might need for tomorrow today. So stay tuned. I will have that out by 1:45. Thank you.
Okay. All right. So that said, let's go ahead and move forward. So whenever you're separating charge, it actually does require work to do so. If you remember our definition of work equals force times distance. And so if you're forcing two objects together and pushing them through a distance, you're doing work. And that work is actually translated into the separation of charge, the movement of protons and electrons, depending on their affinity for electrons. Okay, so there's some demonstrations that I would do normally, but they're contained in this one. I've got further demonstrations down here too. All right, so here's some of those demonstrations I was talking about. So we use this machine called a Van de Graaff. We've got one here at school, and it uses friction. And so what happens with the Van de Graaff is you end up having this rubber belt that goes around in circles. And as it goes around in circles, there's this little metal brush down here, and it causes just like a frictional situation that it transfers charge. And so in this case, what it does is it transfers like the electrons in a circuit that goes out to this wand over here, and then it makes a positive charge form on this top of the Van de Graaff, and it creates like a differential or a voltage between where the electrons are stored. You'll see this in this video right here to make sense of that. Okay, next one here is called Coulomb's law, and this is really dealing with this idea. Okay, we've got charges, and these charges, when they're separate difference from each other, they actually start to put forces on one another. And Coulomb, this guy back in the 1700s, he came up with this idea of how does the charge separations cause forces, and how do those forces relate to like how far they're separated and how much charge separation there is. Okay, so Coulomb's law. One of the things that it just says that the force, well, let me get into it. I'll go to the next page. I don't have it on this page yet, so sorry. One thing to notice here, there's a connection between how the gravitational force works and how electrical force works. Since last year, we did quite a bit of work around how does gravity work. If you can remember that equation, the force of gravity equals big G, the universal gravitational constant, times the product of two masses divided by the radius, or how far they're separated, squared. That whole equation we did is just like the Coulomb's law. It's pretty much set up the exact same way. But one of the big differences is electrical force is actually 20 orders of magnitude stronger than the gravitational force. It's very, very, very strong by comparison. Okay, why don't we experience a massive electrical force as we stand on this planet right now? Okay, the answer is down here. Check it out. What do you think? Okay, now Coulomb forces, when you put charged particles next to each other, depending on how close they are and depending on how strong the charge is, you get forces of attraction and forces of repulsion. And you want to be able to make predictions about what those forces look like, and we're going to use vectors to make sense of that. Okay, so notice I've got two positive charges. What are they going to do when they're placed next to each other? A positive and a negative, what are they going to do? Negative and a negative, what are they going to do? Okay, next one here shows you, okay, these are vectors, right? So I've got this acting on this one for repulsion, and you can kind of see the vectors here. These are acting with attraction, and again, these are with repulsion too. And just kind of noticing directions, noticing magnitudes, how does that work? So here's the technical equation for Coulomb's law. So you get this in your equation booklet, but just here it says here that electrical force equals KQQ over R squared. and the K is a constant called Coulomb's constant. It equals 9 times 10 to the 9 newtons times meters squared over Coulomb squared. And this is a universal constant. Okay, this basically says that because of this fundamental force in nature called the electromagnetic force, at any sort of given charge, okay, call it 1 Coulomb, separated by any given distance, call it 1 meter, okay, it's going to produce a force in newtons that is in proportion to this universal constant right here. Okay, so this number is going to come up a ton, and you're going to want to use this number quite a lot. It's called Coulomb's constant. It's in our data booklet, and you should just memorize it pretty much because we'll use it so much. Okay, all right. Now, there's also another way to look at this idea of K, the K value. It equals 1 over 4 times pi times the emissivity of free space. And I'm not going to even go into any details of this. We're not going to really do much work with it, but I just want to notice this is in the formula booklet like this. And if you had any question that asked you to calculate the emissivity, you could just replace K with this here, and you could figure it out. But I'm not going to go into any more detail because it's very complicated, and you don't need to know much about it. Okay. Next thing, it talks about this concept called superposition, and this is really vector analysis. Quite a bit of what we do with static charges when they're near each other with static electricity. We calculate through vector addition, attraction and repulsion. And so notice, like, for instance, if I have these two negatives right here, okay, they're going to repel. And so you notice how I draw a line of force here for electrostatic repulsion. Now these two are going to attract. So I draw a line here for electrostatic attraction. And based on the values of these things here, how much charge do they have, using force calculations with Coulomb's law, force equals KQQ over R squared, I could figure out the size of these relatively based on their force. And then I could just do some vector addition and figure out the net force. Okay, and you'll see we're going to practice this. So first practice, you've got a negative with 4 positives equidistant around. What would the charge be? Check it out. Makes sense. Okay. The next one is a pretty complicated problem. I want you guys to work through this. This is part of our practice that we're going to do too, where it shows you different charges in a situation where they actually are in a square here. Okay, so notice that this is like a square. And so because it's like a square and this is right in the center, I have an angle here that's going to form a little triangle here. And that little triangle is going to be a 45, 45, 90 triangle. And based on some of the math around 45, 45, 90, you can actually use Coulomb's law to figure out what would be the net force this thing would experience. Okay, because you can imagine it's going to be attracted to this one and attracted to this one, right? These two charges are the same, and so that means that it's going to be attracted in the median between the two, or straight upwards. But then when you want to figure out, well, how much attraction is there? What is the force? What is the K constant? What are the charges? What are the radius? You want to put it all together with vector addition, and I've given you clues on how to do it, and I've solved it all the way through with you, and there's a practice problem on one of our sets. Another practice problem here has to do with 2 balloons right next to each other. Now you can imagine that gravity is pulling these balloons down. Okay, why are they held apart? The reason they're held apart is because there is a force of electrostatic repulsion. Okay, they're being pushed away from each other. And you can do vector addition by looking at this triangle. So I got a triangle right here. Part of my triangle has a net force going that way, repelling. Okay, part of my triangle has a net force pulling down. Okay, based on gravity. And if I just draw that triangle there out and I use electrical force for the X part of it and gravitational force for the Y part of it, I can do some vector addition and just figure out what is the charge on each balloon. Okay, so you're going to see the math. I've worked it all out here for you. And then you'll see it in our practice problems, working through those kind of vector problems. Okay. All right, now as far as like understanding how electrons move in substances, we're going to get into this a little bit later, but there's something called semiconductors, which we'll look at these with things like resistors later on, but these are semiconducting materials. They're not like perfect conductors or perfect insulators, but they have a tendency to slow down the movement and control the movement of electrons in circuits. We'll look at this a little bit later. There's also something called superconductors. These superconductors are usually made out of like rare earth materials that have been put to extremely cold temperatures, almost close to absolute zero. And these superconductors basically have like zero resistance inside them. So normally, like when you flow electrons through a wire or something, it does run into resistance, causes heating to happen, it slows down, it causes you to lose energy over distances. But with superconductors, superconducting. There's no resistance. Okay, but then the main thing we're going to start focusing on now is this idea of conductors versus insulators. So conductors have free electrons that can move around. Okay, so like metals, for instance, they've got their lattice of the metal nucleuses all over the place. Okay, but the electrons around the outside of these nucleuses are free to just go from one to another, and so because of that, they're freely able to move. Electrons are through metal. So these are called conductors. Insulators are the opposite of that. The electrons are like bound tightly to their nucleuses. These kind of compounds right here, they don't allow electrons to move. And so when we build circuits, like things like a wire, we're going to put the conductors on the inside of this wire to move electrons really well. And then insulators, we're going to wrap them up so that the current doesn't come out and electrocute you when you're touching it. All right. Okay, now this all brings us to this concept called electric field. So electric fields are just regions around charged particles where the force can be exerted on other particles. And it's represented by field lines. And so what we see is like if you have a positive particle, you can see these field lines emanating out and away from the positive particle. And when you have a negative particle, you can see the field lines going toward the negative. Field lines are vector quantities. So you notice the arrows right here, and they follow vector rules. Now, I have a FET here to play with, and you kind of check it out. Now, you're going to want to memorize these rules about how fields work. But if I take like a charge, like a positive charge, and I put it out there, you're going to notice that the field lines go away from the positive charge. Okay. If I put the voltage on there, okay, you can kind of see the strength of the field is like the dark red, and then it decreases with distance. Okay. And then I put a negative field on there, and you can play with this, and you can see that all the field lines go into the negative charge, and you can see its strength too. And then as I get these closer to one another, okay, you can see that they're sort of canceling each other out there, but then they grow back out again. You can notice that there's like a field line going between the positive and the negative, and you can see these lines. And this is like where the drawings for field lines come. You can see if you were to connect like a line to a line to a line to a line, you kind of see how these lines form here. Now, if I were to go ahead and put two positives there, you can kind of see in the middle, it actually creates an area where there's no field right here. It's like a zero field. So I want you to play with these here and get your sensors on there too. Okay, this is like our test charge. And a test charge, when you put it on there, it's going to show you how the force works. So what is the strength of the field at any given point? And as you get closer, it gets much stronger, and you get further, it gets further away. And so the field lines are really created by this test charge right here. And you put this test charge somewhere in here, and this test charge, which is defined as like a positive charge, but the charge is so small that it doesn't affect the field. Okay, it's just like an imaginary thing we make up to test the field, but because it's positive, you can see that it's being repelled by this positive charge. If I put a negative charge over here, you can kind of see the field lines are going to be attracted towards it because this is like a positive particle, and the field is proportional to distance. You can see the vector arrow going higher, get further away, get smaller, and it's always changing its direction, and that's how we define the field lines. All right. All right, so next slide here shows you a picture of the positive charge in a field, and this is how we come up with these drawings in the first place. Now, there's a good little demonstration here. Shows you how some charges are being attracted to this balloon. Check out this video. It's really interesting. It's a demo that I usually do in class that kind of shows you this idea of electric fields and polarization. All right, next one here, rules for electric fields. So electric fields, again, we're defining them by the positive test charge being placed around somewhere and seeing what the effect is on that positive test charge. Because of the way that the positive test charge is pushed or pulled, it gives us our vector direction, and the strength at which it's being pushed or pulled gives us the magnitude of the field. And so this is kind of how we define a field from these charges. Here's your rules for a field. We always start with positive charges, and the field lines go out. Negative charges go in. Field lines never cross each other. They exit surfaces at 90-degree angles. The density of the field lines talks about the density of the strength of the field. If they're far apart, they're weak. If they're close, they're strong. And when you have a conductor, the inside of a conductor has no field inside it, but the outside does. When you have objects that have heavy curvature, you're going to have stronger fields around the areas of heavy curvature and weaker fields around flat areas. So these are all just some rules of fields. I want you guys to know how to draw fields, but the main things I want you to know how to draw is draw fields where you have like charges, and you notice there's zero E field in between them. I want you to be able to draw fields that have opposite charges where you have strong field lines between them. And then when you have charged plates, you end up with what we call a uniform electric field between them. Now, what I mean by uniform field, then if you test your field strength at any point inside these area between these two plates, it's going to be the same number. It doesn't get stronger as you get closer to these plates. It stays even the whole way through. So flat parallel charge plates create uniform E fields, and we do quite a few questions with uniform E fields. So just keep that in mind. But memorize those three types of drawings. You'll see it on your practice problem set. There's this thing called the Faraday cage. You can check out this video and see how they work, but it's kind of fascinating. Check it out, see how it works. So this thing called electric field strength. Now we actually have a quantity for it. I've been talking about generically with field lines, but we can define it as the force per unit charge exerted on a positive test charge. And notice like here's between two plates, here's that uniform field I was talking about. And this positive test charge here is asking, what is this electric field doing to me? And I can tell you that because it's positive and that's positive and these field lines go down, it's going to fly off in that direction. Okay, it's going to move, so it's going to be forced down there. So this refers to electric field strength. Electric field strength, we give it the capital letter E, and we define it as the amount of force per unit charge. Okay, force over charge, right? Now this equation, you're going to mess with it. What is force equals EQ, okay? Here's a question where you're going to figure out what is the answer to the question based on that formula there. And I put the answer in the bottom. Make sure you can do that for kind of a problem. When we also look at substituting in this equation force with the electric force as defined in Coulomb's law, I can take E equals force over charge, and I can wash it down to this equation, KQ over R squared. Here's a problem to figure out that one right there, and here's the math. Make sure you can do that math. Same thing with the electric field equation. You'll see questions where you have two charges, and they'll ask you if you place a point equidistant between the two charges, what will the field be? And if you notice, it gives you two equations together because you're looking at this force and that force. You've already noticed that the positive charges, the charges are always, test charges are always positive. It's going to be like repelled from this one in this direction, but repelled from this one in this direction. It's kind of like being repelled in two directions at once. And so it's going to sit there because of it. And so because of that, it's going to create a zero E field. Okay, so you'll see conceptual questions trying to fool you with all these numbers when the answer is actually just zero E field. But when we have a different type of a question, like this one, where we actually have a positive and a negative, this charge here, because it's still a positive test charge, is going to be attracted this way, but also pushed this way. And so there's actually two Coulomb equations together, where one's pushing, one's pulling. You add the two equations together. I show you the math of how to work it out right here with the answer. Make sure you can do that problem. You're going to see these examples on our practice set. Here's the last question right here, and that is it for the day. Okay. Now the practice set you get along with this, you're going to see some practice problems, and you're also going to have a reading comprehension to go with it. The practice problems aren't due until after break, and so you've got lots of time to work on it. But yeah, go ahead and work through this concept today. If you have any questions, you can get in contact with me and just let me know. But you guys have a really awesome day. Enjoy yourself.